Hi, everybody. Let's just quickly go through the definitions again of an annuity. So, for an annuity, it is a series of equal payments made at equal intervals. Now, it's important that we're making equal payments at equal intervals because there is some sort of regularity that has to happen for it to be an annuity. There are different types of annuities, but the ones that we're talking about here in this course are only the ones that happen where you pay at the end of the month. And another word, amount of the annuity, this is the sum of all of the payments and the interest rate at the end of the annuity. So just to clear those things up, we're going to be referring to all of those words often in this unit. Let's do an example. Romel is saving to go on a luxury vacation to the Caribbean. Today is June 1st, and he decided that at the end of the next 6 months, he's going to put aside $200 towards his trip. He found a special savings account that gives him 12% compounded monthly. How much money will he have at the end? Now, think about this in terms of compound interest. It's like he's saving money, but each month will have a different amount of interest by the end of the period. So before we go on, I'm just going to take my interest rate of 12. Because it's compounded monthly, I'm going to divide it by 12. And my interest rate per compounding period is 1% or 0.01. So today is June 1st, and Romel is going to save money for the next 6 months. I'm just going to write that down. So we have June. This is month 1. Then we have July. That's month 2. August, month 3. September, month 4, October, month 5, and November will be month 6. For each of those months, he's going to be putting $200 into the bank. Now, if Romel decided to save his money by putting it into a shoebox and putting it under his bed, then we could easily calculate that Romel has saved 200 times 6 or $1,200 by the end of the 6 months. But since this is not the case and he's getting interest from the bank each month, we have to calculate the interest for each of these months. Now, we defined that an ordinary annuity happens at the end of the month. So November was the 6th month. He puts it in on the last day of November, and the annuity is over. The agreement with the bank for the annuity is over. So the $200 that he put in November has no interest. The amount that he contributed on October 31st, it got 1 month worth of interest. So I'm using my compound interest equation. A is equal to P times 1 plus I to the power n. So we have 1.01 to the power of 1 because he's getting 1 month worth of interest. The amount that he put in September, we'll get 2 months of interest. So our N is 2. August, $200 times 1.01 to the power of 3. He's going to collect interest in September, in October, and in November. The money that he put in July, $200 times 1.01 to the power of 4. And June, the money that he put in will have collected 5 months worth of interest. So if we want to know how much money he's going to have at the end, we're going to take all of these amounts and add them up. So to get the total, add right, I'm going to throw this all into a calculator. 200 times 1.01 to the power of 5 plus 200 times 1.01 to the power of 4 plus 200 times 1.01 to the power of 3 plus 200 times 1.01 to the power of 2 plus 200 times 1.01 to the power of 1, and then our last month, which got no interest and just 200. In total, we have $1,230.40. So let's write it down. The amount here, $1,230.40. Now, because he decided to save with the bank and not with the shoebox under his bed, he's earned $30 in interest. And we know that altogether, he invested a principal of $200 times 6, which is equal to $1,200. Now, $30 isn't a whole lot. In fact, it's not very significant when you go on a trip, but having some money is better than having no money. So I would say it's still worth it and safer for me to put it in the bank, get the $30 of interest versus putting it under my bed. Now, this is one way to calculate an annuity. I had equal payments made at equal intervals, and I calculated the interest that I would get in each month. But sometimes when I have an annuity that has so many periods, it would be incredibly difficult. So we can use an equation. The equation that we use, the amount of an annuity is equal to the payment times 1 plus I to the power of n minus 1 divided by I, where A is the amount of the annuity, R is equal to our regular payments, I is our interest per compounding period, and N is the number of compounding periods. So if we go back to the question of Rommel, we could use our equation to solve for this question. So our equation, A is equal to R times 1 plus I to the n minus 1 divided by I. What I need to do is I'm going to write down all of the values. So A, I don't know. That's what I'm looking for. My regular payment is $200. I've calculated my interest per compounding period to be 1%. And the number of compounding periods is 6 because he saves it for 6 months. So I could put this into my equation. A is equal to 200 times 1 plus 0.01, close bracket, to the power of 6 minus 1, close bracket again, divided by 0.01. I'm going to substitute all of that into my equation, and I should be getting the same amount that I calculated when I drew out my whole diagram. So 200 times bracket 1.01 to the power of 6 minus 1 divided by 0.01. And I do have the same amount, $1,230.40.